Hi, in this tutorial we're just going to go on about the conformations of organic compounds. I think it's quite important to cover this topic actually, because a lot of people get stuck at the early stages about how to draw molecules and what the different representations are. So I'm going to try and draw them as best I can, and if you go over to if you're on the website, then you'll be able to see the ball and stick models and manipulate the structures in the 3D model viewer anyway. So if I look at, for example, this molecule here, so we've got, I'll draw the original structure in blue, CH2, and draw another one, CH2, Cl is there, okay? So we've got 3 chloro, 1 propanol, okay? So there's a propyl group there. There's a chloro and there's the alcohol bit. Okay, so I can draw it like that, but it doesn't really tell me anything about its 3D structure. So let's see if we can draw it in 3D as an organic chemist would like to draw it in 3D. So I'll use a black pen for this. I'm going to whiz the chloride bit up there. So if I draw CH2, put the Cl there, and then move it down like that, C there, C there. Now I've got to try and draw these hydrogens on. So that's one hydrogen there, another hydrogen there, and I could have done the same for this bit, but I've left that because I just want to draw it a little bit simpler than it needs to be. And so these are all in the plane, and then draw the other hydrogens of this atom here like this. So that's one way of drawing it as a 3D structure. And what does this mean? No, this means this is coming out of the page and this is going behind the page, and so on and so on. So that's like a 3-dimensional structure. So that's a dimensional structure. This is just the linear sequence, if you will, of the molecule. Now if we took that and then did a ball and stick model, what would that look like? Well, we'd have to represent these carbons here as a ball and stick. So I just draw a big ball, which gets a bit confusing now because I'm drawing what looks like oxygen. So let's just get rid of that. Let's choose a different colour for the balls. And I'll choose choose this nice pinky colour. Okay, I'll draw them a bit larger than normal. Oh, that didn't work. Let's undo that. And let's choose that colour again. Okay, so that's that carbon. Choose that carbon, and then we'll just want to try and draw it like a ball and stick model. So that one would be coming out, so that stick out like that, hydrogen, and then we'd have that hydrogen going back, so that come out like that, and then we'd have. So this is a bit easier to see now. That'll be CH2Cl, and then we've got this one here, and that's pretty much in the plane of that, so just come out there like that. OH. This hydrogen's sticking out, and that one's going back. So you can see what I've done here. I've just replaced these carbons with these balls, so you can see that it looks a bit more 3-dimensional actually like that. But as organic chemists, we tend not to draw things like that. What we tend to use is what's called a Newman projection, which is what I'm getting to. So imagine picking this up and looking straight down here. So draw that. So there's my eye. And I'm looking straight down here, like that. Okay. That's what I'm trying to do now. So I need to look down there. And what the Newman projection is really good at is actually looking at, if you've done the Carlin Gold prelogue tutorials or things like, you can actually look at stereo centers and things like that and assign them based on this method. It's really useful and powerful method for looking at a 2D version of a 3D molecule, really. So let's have a look. We'll call this number 1. So that's at the front. So in Newman projections, the front part of the molecule. Let's see if I just move all these across a little bit, and I've got a bit more room. Just grab them all and shift them over there. I'll just shrink them down a little bit, give myself a bit more room. So in the Newman projection, so right Newman up. Okay, Newman projection. The front bit of the molecule is represented with just lines like that, and that dot there is that carbon, and I'll label that up as 1, so I call that 1, and that 2, so that's 1. Okay, and the back carbon is represented as a I'll draw it here first. That's the back carbon, it's represented as a circle. Now if you look at the way I've drawn that, I've put these hydrogens like just not overlapping these ones here. So if I drew it like that, that'd look like that. And if we put the rest of the parts of the molecule in, we've got CH2 Cl there, and we've got a H there, we've got a H there, and if we draw the back bit in, we've got a H there at the top, a H there at the top. Remember, we're looking right down this way, OH. So if that was an R group there, then if we look down it would be that one, that would be the R group. Okay, so that's important as well to know which one's on which side. Right, so that's no good here because it's broken apart at the moment. So if I just change the colour of the back bit, actually, we change that to green, and what I'll do, I'll just group these together so they don't all fall apart. Group that as well. Right, and I've got to put the number on. I'll put the number on, so that's number 2, yeah? That's number 2 there. So I'll put that just to the side there so we can see it. And then I'll have to group that again, won't I? Okay, so that's number 2. Now what we need to do is pick this up and put it on there, or pick this one up actually because this is the front one. Put that over the top of that like that. Okay, so now you can see the one at the front is this bit, and the one at the back is the green bit. Now, good job I chose different colours because it would have been a bit confusing, but when you draw them, obviously you're going to draw them in the same colour. You don't have to, but you can do. So that's a Newman projection, and that's really good way of looking at the 3D structure of a molecule. Now, if we just basically look at the way the molecule rotates and things like that, if we look at the configuration I've got here, I've got all the atoms of the adjacent parts of the molecule are anti to each other. Okay, so they're not overlapping with each other. So that's the lowest energy configuration for that molecule. So if we rotate around this, so this is anti at the moment, so anti, and I'll put these up at the side. That's the anti configuration. Okay, and I'll just get rid of that because I'm going to rotate it now. See if I can do this. Okay, so what's going to happen now is I'm going to rotate it. Let's see if I can do this. Oh, here we go. I'll try and grab that. That's it. I'm going to rotate it now around that point. It's not too bad. It's not brilliant, but not too bad. Okay, so I've rotated that bond. Basically, I've rotated around this bond here. Let's just draw a little arrow, then you can see what I'm doing. So I'm rotating around this bond here. Okay, and in doing that, these are now eclipsed. Okay, eclipse, just like the lunar eclipse or the solar eclipse. Yeah, we've got with these are overlapping. That's actually quite high in energy because if you think about these, the electron clouds around here, then these electron clouds interfere with each other, and that's why you get like steric hindrance and things like that. So that actually increases the energy of the molecule as it rotates. So as it rotates again, if we do another one, so I can grab this, you rotate it again, you'll find, I'm just trying to, my centre's not quite right, rotate again and they'll become anti again. Okay, so you're basically going from an eclipsed, an anti, an eclipsed, an anti. But if we just rotate it a little bit more here, in this configuration, as we rotated it all the way around, so that one's gone all the way down to the bottom, this CH2Cl group is now overlapping with the OH group, and that is the highest energy because there's a lot more electron density around these parts of the molecule than the hydrogens. So when the hydrogens overlap, you do get some kind of energy increase. So what I'll try and do now, I'll just clean this up a little bit, but what I'll try and do, I'll just make it the lowest energy configuration. Move that up. Okay, so that's pretty much, just move that a little bit. That'll do. Okay, so that's like the lowest energy configuration. That one's the furthest away from that one. If I draw a graph, so we're nearly finished now. If I just draw a graph, let's choose blue for the axis, and this is energy, say, and this can be the rotation around the bonds. Okay, so that's degrees. That's not very good. I'll write dig for degrees. Okay, that's supposed to be a degree symbol. Okay, looks more like an at symbol now. And there we go. Okay, so if we look at the energy as it moves around, that's the lowest energy configuration there. So let's just put a point. And then as I move through, it went high, and then it went to a low again as it became there. But then as it got to this bit, it went the highest, if you will. So it overlaps there, it goes to the highest. And then it went into that gap again, so it went to a low. And then it overlapped with the hydrogen, so it was like that. And then it went back to the beginning. Now if I draw that as a graph as it's moving around, have a look what we get. So it goes up, and down, up, and down, and up, and down again. Okay, so you've got like a sinusoidal type of pattern where the energy increases and decreases, but because these are not symmetrical, so alright, if this was ethane, for example, then as it passed this bit here, so ethane is this, isn't it? No, it's not. I don't even know what ethane is. CH3, there we are. Okay, so if that's ethane, as this passes through, that would be a hydrogen there, that would be a hydrogen. This would be symmetrical, so you'd have, let's try and draw ethane in different colour with a dashed line. Okay. Then the energy of this bit would be like that, wouldn't it? Okay, so it actually, in this bit, be the same level, because it's going through another hydrogen. But because we've got this chloromethyl group there, and we've got an alcohol group there, then you get more energy to pass that barrier there, and the energy increases the closer you get to it, and then it just fades off again. Okay, so that's basically the looking at Newman projections as an excellent way of drawing organic structures, and also a brief introduction to the energetics around a carbon-carbon bond as well. Now at room temperature these will be whizzing around each other, but just gives you an idea that there is some energy barriers to be overcome when drawing these. Okay, so I urge you to have a go at these, and I'll try and put some worksheets up and things like that for you to practice. So that is conformation of organic compounds, especially with respect to Newman projections.